here I would like to say that this equation I have forgot made some mistake here, like it was an incomplete one, like the other it here you should have one I k q term, right, plus like other field you will have here what you are you can expect here you will have l k q g with I g, right, plus another term I'm writing here that should be L K Q K Q I Q, right? Not I Q, it should be like I K, yes, L K Q. Uh, it should be L L, sorry, it should be like L K Q I Q. Fine, L K Q Q Q I Q. Anyway, you can figure it out. You people are quite intelligent. So, interestingly, what we are getting here that is very, very important. This matrix here, you can see that I have written all the columns so that you can figure out. Uh, First three columns IQ, ID, I0, they are the corresponding means are related to stator variables with in rotating QD0 frame, sorry, in QD0 axis, and the remaining four columns, the last four columns, they are associated with rotor variables. Now let us see the entries of these matrices. As we can expect that lambda q, it only depends on, from this matrix what I can see, it only depends on IQ. Here also you can see that this one, this is what FKDGKQ. That means the first column due to IF, second column IKD, third column this one, this hot means in your total matrix it is sixth column, this is due to IG, and the last one, seventh column, is due to IKQ. So here, as we know that q axis are orthogonal in position to d axis, means perpendicular, they are in quadrature. That is why you can see that only LSG and LSQ are present in your LQ equation. Similarly, in your LD, here you can also see that this LD is dependent on, means ID, means when you are talking about lambda D, the D axis flux linkage, you will have LD ID plus LSFD, LSKD. So one thing you must find it out here, that is very interesting to note, that if we consider uh, whether the matrix is symmetrical or not, what we will find that here, sorry, here this is this element, that is this element is LSG, sorry. However, if we come here, means I'm talking about these two elements. One is this LSG, another one that is at 6-1 position, that is 3 by 2 LSG. Now having this 3 by 2 term is a bit annoying. That makes the whole thing means asymmetrical. We cannot means transpose this matrix and we cannot claim that transpose of this matrix will result the same matrix, but it is our means it is desirable that when you are having this lambda q, lambda d, lambda 0, it is not only the removal of theta dependency on your inductance model, but you should think how you can make it a symmetrical one, that because symmetrical matrix makes it more handy, and means in during computational cases it reduces our computational efforts also, right? So in order to make it means symmetrical, what we have done here, we have just annoying terms that or means that makes it's asymmetrical, this 3 by 2 factor. What we can do here, it's we can apply some transformation technique, like we can have some virtual variable like if dash, ikd dash, ig dash, and ikq dash, because if you see this matrix, all these are coming here while we are considering corresponding the entry for our this means all these 3 by 2, this 3 by 2, see where it is appearing. This 3 by 2 is appearing when we are considering the contribution of like iq and id on our means lambda. Now can we do some mathematical manipulation, like this position 6 1 and sorry, this position is 1 6 and 1 7, this position 1 6 and 1 7, keeping them intact. Can we do something to appear a 3 by 2 term here in 6 1 and 7 1? Like what I'm trying to say, can we do some mathematical manipulation so that we get a 3 by 2 here, a 3 by 2 multiplication term here, as well as here also, because we need them, right? So that this can be done. How we can do this? uh, if we make our current two-thirds of its original value by developing some virtual current like if dash, ikd dash, ig dash, ikq dash, then you can understand that we must, in order to keep the flux linkage unaltered, we must allow our means appearance of 3 by 2 here in 6 1 and 7 1 term, right? Now see, that is what we are getting here. So with this one, with this modified uh, definition of current, what we are getting this matrix. I'm not ready to waste time on reading the entries of this matrix. You can figure it out by yourself. This is very simple, and also don't means I know that I have already means delivered a lecture for at least say almost 1 hour, and from the very beginning you have been thinking about that what kind of question you are going to get in the examination. So let me assure you that you don't have to write all this matrix equation in your examination, but what you need to know and what your question will come, that you can skip the matrix, but the idea about the elements, like here you must have you may not know that this is 3 by 2 lsg lsf, you don't have to remember, but what you need to remember that lambda d can only depend on id, if, and ikd. It cannot depend on ikq, ig, or IQ. That type of things will surely appear in your question. Similarly, here you can see also this I0. Why this I0? Why there are no other term, means no other ID, IA, IKD, no term is there? I may ask you this kind of question. And also means logical explanation or a few simple derivation that I'll let you know. I'll give you one assignment, and there is a chance that you can get this kind of assignment type of question in your final exam. So here, this total thing, it's you can figure out. And as means, if you have common sense and you are willing to understand, it's very easily understandable. I'm not wasting time here. So what we are getting here, like expected, now this is perfectly symmetrical matrix with all 3 by 2 entries. Okay, now instead of having it on our means uh, rotor, means see here, one thing it's true that we are having all this quantity, means what is the position of your QD0 axis? It is rotating, it is attached with rotor and continuously rotating. But if we want that, like if we want to express all this term, like everything that this IQ, ID uh, are, means now we are having a symmetric matrix, but means can we do something? Can we do something to means refer the whole, means all the things in stator, means not means bringing them back on the stator reference frame, but just the magnitude. We are interested in magnitude. So if a rotor current is having a means a QT0 frame that is attached with rotor is having a current value, say like IA, then how this IF can be so adjusted to get a corresponding means current value when it is referred to stator. But while referring to stator, here we are using just transformation, transformer action. We are not going to consider any kind of speed or any other effect in the picture. We are only interested in magnitude. Now, you may ask me that what is the rationale behind this? And this question should come to your mind also. And before I answer, I would like to hear your means take on this particular issue, right? So this IF double dash, like you can see that in case of transformer, what we know that generally V1, sorry, by V2 is equal to N1 by N2, right? And in case of I1, I2, what we know, I1 by I2 is equal to N2 by N1, right? N2 by N1. So this formula will apply over here, like when we are transferring IF double dash, you will see that this NS, this is the stator winding turn, and NF is the field winding turn, we are obtaining this ratio. So we are getting a term that is referred to our stator, IF double dash. Similarly, we are getting IKD double dash, IKQ, IG double dash, and all other terms we are getting. So when we are dealing with voltage, then NS is coming at the numerator, and when we are dealing with current, that NS is appearing in the denominator part, right? Likewise, what happened in case of flux linkage? In case of flux linkage, it is very obvious that it will follow the means uh, pattern of voltage, because your voltage is proportional to your flux linkage. So obviously, if your voltage follow V1 by V2 is equal to N1 by N2, then your means flux linkage will also follow the same. So here we are getting this for flux linkage. What about the resistance? Resistance are following the same principle that we know that for impedance transformation from one side of transformer to another side, we are applying the same formula here, right? And the same is true for our uh, uh, means individual winding uh, inductance. Here you can see there is a slight difference, that while we are trying to refer what is happening, that the turns ratio, this NS is coming to the denominator. Now let me ask you one question, that why this NS is coming means, and the denominator means, why not it is appearing in a numerator part? So you should think and you should answer me that why this NS, this is here, this NS is appearing in the denominator, not in the numerator, right? So please note down, I have asked a lot of questions here while delivering this kind of lecture, and I know that is you people constantly ignore all these means questions, and later on ask me that, sir, how to solve those kind of true false questions. But all the true false question answers are, I mean, inside all this discussion. If you take part in this discussion, you will be benefited, right? Now here you can see that while LSF is like this, LFF dash LMF, these are having a different equation. uh, Here NS is appearing in the denominator part also, right? So you think about all these LMS, and then you please get back to me. These values are important if you someone of you do project on this synchronous machine control, then you may need all this expression. Also it is available in this book of Chi Wang, right? That Kim Nong book I have already sent to you through Litris portal. And these are the all the VQ, PD, P0. These are the voltage equation. All the voltage are having IQ, ID means. And here again, I would like to tell you or like to remind you that here these P are not pole, rather this P is right. So don't forget that P indicates time differentiation, or P is an operator that indicates time differentiation, and all your flux linkage, current, everything is referred to stator. We are having 7 voltage equation and corresponding 7 flux linkage equation with us. So with this we can have our circuit model. Take q axis. What is our q axis equation? This is vq is equal to RSIQ plus uh, lambda. Sorry, I have made one mistake here. Very sorry for this. This term here. Let me correct it. While deriving, I have made this mistake. It's means more or less okay, but here these two I should write, means instead of writing p theta r, here I should write like omega r. Basically this is the speed EMF, right? This last term is speed EMF. So here, like we expect, it is already in that form. Now see, can we have the corresponding q-axis circuit model? See, while we are talking about q-axis, what are the elements we need to consider while developing a q-axis circuit model? That are like this equation vq. Then we must consider this vg double dash and vkq double dash. Okay, now with all these, see here, while we are considering this vq, uh, please note that the book from which I have taken this snapshot, they indicate this single dash. We should consider it like all are, means all these are having double dash term. It is vg double dash, this is ig double dash, rg double dash, lg double dash, and also vkq double dash, vg double dash. Fine. Now see here, uh, if we think about the linkage between, or the, means uh, how these three voltage are related to each other, then you will see that this vq, it is the only inductor lmq, they are common. It means if we consider their corresponding flux linkage, then we will see in lambda q there is one lmq, then in lambda g there is another lmq, and also in lambda qq there is one lmq. So all these are connected, and here this mutual inductance is the connecting link of all these. So what we can write basically here, see this one, this omega lambda d, or in our way it is omega r. It is not only omega, it is omega r lambda d. This pdmf, it's like back emf, it is opposing your vq, right? And you are having rs. This rs is as we have considered, this rs is equal to means here we have considered rs is equal to ra is equal to rb is equal to rc, right? So this RS is means you are considering a balanced network, and this is how we are getting this RS value. Now this omega lambda d, it is actually not omega, it is omega r, and this omega r is our machine electrical speed of rotation. Now we are having LLS. This is our leakage inductance of our Q phase. Now this LLS also, if we go to D phase, then we will see that LLS and sorry, um, if we see that LLS is present there in D axis also. Why? Because in case of D axis, your leakage inductance remains same. This is also a virtual leakage inductance as means associated with two virtual windings. But as we are considering this QD, means Q and D, they are identical in nature. So you will always get this. Now here you can see this uh, thing, this LMQ, whatever voltage you are getting here due to IQ, this, if you allow the flow of current, only IQ will flow through this. Now, see, here, this lambda Q, then you are having LMQ IG double dash, LMQ IKQ double dash. That means here, in through this parallel branch of this inductor, all three currents are flowing. Your IQ plus IG plus IKQ, right? So all three currents are flowing through your branch now, and accordingly you are having but with other two phase, you can see the other two phase is not having that speed EMF term. I want to mean this one is not present here in this branch or in this branch. Why? Because this means physical position of this G and Q, they are attached to your rotor. And although this Q and D, they are also attached to rotor, but this Q and D, they are means taking care of your ABC quantities or ABC variables. They are stationary frame, means stationary reference frame variable. So while we need to consider this phi q, we have to consider this omega lambda dt. But in case of these two, as they are if they never experience or any kind of such means relative speed difference, that is why you will never get back EMF here for VG double dash and VKQ double dash circuit, right? So we'll in the next part we'll analyze the D phase winding also. Hello. So, like the from the second equation, we can find out the equivalent model, and this P theta r will give us omega r, means the total equation will become lambda q omega r. But please note the sign here; it is negative uh, lambda q omega r. So, with this, here you can see previously it was plus minus, means it was like a back EMF that is opposing VQ. However, in case of lambda D, here you can see it is minus omega r lambda q. Here it is actually means playing a role of means it is boosting up your means voltage that you are applying here, VD. Now you must think that why in case of Q axis it is opposing the uh, input voltage, while in case of D axis it is means uh, acting in phase, and it is basically supporting your VDA axis. Means this omega lambda q basically, if forget about everything, if omega lambda q and Vd they act together, then what you can expect here from this equation, it is evident that it will increase the magnitude of id. From this equation only we can say, right? So what is the logic behind this? uh, I expect this question from your end also. Now see here, uh, like rest of the things are almost similar like our previous model. Like Q, in case of Q, that one was LMQ. Here it must be LMD. Previously it was LLG double dash, RG double dash, and with damper widening it was LLQ double dash and RLQ double dash. Here it should be like LLKD double dash RRKD, means everything is now associated with your D axis winding. Now, uh, so one question that I'm asking you, that why in case of Q winding it is this speed EMF is opposing, it's acting like a back EMF, but in case of D axis it is acting like a EMF that is means assisting or boosting up your means applied EMF. Now come to zero sequence one, that is the most gentle network. It is only RS and LLS, that is the resistance and leakage inductance of your zero sequence network. It is free from all sorts of mutual thing, right? Now we must investigate what is the amount of total input power. So input power, while we are trying to find out the total input power, here how to obtain it, we must do it like, the question is that why there is no term, like no such term like VKD, IKD or VKQ, IKQ. The answer is that if you see those windings, the damper winding terms cannot come in the power equation because damper windings are short circuit. So you will understand that every instance it is bound to happen, right? Now what we are having here, that omega r is equal to d theta dt omega t, that is the speed of our rotating reference frame qd naught that is attached to our rotor mechanical body. Although this omega r is, again I'm telling you, it's electrical speed of rotation. So here we can write, as we are considering this is a case of a motor, since it is a motor, so the power is flowing towards the machine, means from source to motor, like the input to motor. That is why here what we'll observing, that uh, for our own benefit we are converting this equation in qd not coordinate. Now see, here we are the input term, these are the loss term, right? These are all these are the loss term. Now here one thing you must understand, that these two are 3 by 2 rs, this one is 3, means I'm talking about this 3 by 2 that is associated with D and Q axis ohmic loss. Now the other term like RF, RG, they are free from it. Why? The obvious answer is that this IF square RF, IG square RG, they cannot contribute. Why? They cannot contribute like this input power, right? This input power, whatever we are having here, this IF square RF and IG square RG, they are sorry, just I was a bit distracted. Let me tell you once again, IF square RF and IG square RG, these are due to two single phase DC voltage, right? These are for your means reference. What is RF? RF is your field winding internal resistance, conductor resistance of your field winding. What is the physical placement of your field winding? That is placed on your D axis or attached with your D axis. And similarly, this RG, that is the internal resistance of your G winding, and it is associated with your Q axis field winding, right? But this this is, if you see the equation of transformation, that KSR matrix, I'm talking about that KSR matrix, right? It was some 2 by 3 terms was there. Then here it was like first term was cos theta, then it was cos theta minus 2 pi by 3, sorry, not this, right? The term was, let me write once again, it was like was 2 by 3. Here I am writing only the means first column. First column of this KSR matrix is associated with a phase, that was cos theta, then sin theta, and then here it is half, right? So this one, this half means this, so you can understand that why it is 3 by 2 here, this 3 by 2, and why it is 3 here, this I naught square are not, right? So but what about the other term? The few things obviously will come in our mind, that although the damper winding voltage is 0, but no one can claim that damper winding current is 0, right? Means what I'm trying to say, although VKD and VKQ are 0, but you cannot claim that IKD, IKQ, they are, sorry, IKD is equal to IKQ, they are, this means equal sign, this special equal sign indicates it is identically equal to 0. That means irrespective of your machine condition, machine operating condition, this IKD and IKQ, this is known as identically equal to 0. Identically equal to 0. So this we cannot claim, and as long as we are not able to claim that, how we are able to discard the term like IKD square RKD and IKQ square RKQ in our power equation, right? But at the same time, that problem with means incorporation of those terms here, that as we have started from our input side, and input voltage across these two windings is always zero, means again I would like to remind you that VKD and VKQ, they are rather identically equal to zero, means it is short circuit, so always it is zero. Now the issue here is that if that is zero, then you cannot means giving them any input. But whatever means resistive loss or ohmic loss takes place during them, because current through them is and it is continuously varying, so obviously you are having some change in current through them, and whenever there is a change in current from 0 to any other value, whether current is flowing in means any direction, it is bound to cause some kind of ohmic loss. But here we can see that there are no such ohmic loss is present. Then my question to you is that who is supplying that ohmic loss, or how, or who is means who is who is supplying that ohmic loss, right? I hope my voice is clear, because writing everything is not possible due to this lockdown situation. There are a few scratch is there on my screen, and I cannot also write it properly, means it is causing some problem. Anyway, now here eventually if you consider that your means mechanical output, then mechanical output or electromagnetic torque, this electromagnetic torque or electromagnetic power, whatever will be converted, that must have a term omega r, right? So we must have to figure out the terms which are associated with this 3 by 2. So this is our means output power. Rest of the things whatever we are having here, we cannot consider them for our means power output. See, obviously try to understand this. We are considering this PEM. This PEM is basically this P make is our output plus P loss, means mechanical loss that takes place in the motor shaft, right? So here you can see that this PEM is 3 by 2 omega r, means now in order to means let me give you one small hint that who is supplying your I square RG, sorry, means let me write the term I square KQ RKQ, and also like I square KDA RD. Who is supplying these two terms? The answer here is, if you observe these terms, like the terms that is due to your means rate of change of flux linkage, and the this rate of change of flux linkage obviously gives us some expression of voltage, and this power. Now this power, undoubtedly this power, these four ticks you can notice, and these four ticks, the four terms the four means if you add these four terms, you will get some value of power, and that amount of power is drawn from your input source, and definitely that also this one. So this power, mm, this amount of power must be means that consumed power must be means somewhere there somebody is means taking care of that power, and then you try to think about that term ikd square rkd and ikq square rkq, right? And obviously, once again, let me tell you why we cannot take any other term in our generated power, because here you can see this is the only term that is dependent on speed, and your output power must depend on your mechanical output or must depend on mechanical speed, because what we know that power, if we write power P is equal to torque T into omega R. So if we make omega R is equal to 0, then this P must be 0. Therefore, the generated power must have a dependency or direct proportion with omega R. So with this omega R, here your omega R, as I have already mentioned, omega R is electrical angle. This is our E angle. Sorry. This is our E angle, and this omega R M, this is our mechanical angle. And as we know that not angle, rather angular speed means it is like previously what we know on that theta E is equal to pole by 2 theta m. So the same thing is applicable here. Here this capital P, not small p, this capital P indicates number of pole. Because capital P is pole, while small p, that gives us d dt, right? Now this term, this TEM is equal to so the torque, finally we get our torque, that is 3 by 2. Here this capital P is again pole, and these are our cross terms. Here one more thing that you must notice, and very interesting, that is your torque is dependent on cross terms only. There are no uh, means that torque is produced by two orthogonal field or cross means magnetizing action kind of things, because here you can see not exactly cross magnetizing but two magnetic field, they are acting in quadrature, they can only produce torque. And that is quite obvious, because you must recall that famous equation that torque experienced by a current carrying conductor was BIL sin theta, where this I is the current that is flowing through our conductor, B is the magnetic flux density, L is the effective length of the conductor that is means experiencing that flux, and this sin theta is the angle between the means the uh, means conductor and means sine of the angle between the conductor and the flux. So it is obvious that in case if we have something like this kind of current carrying means flux, and we have uh, current carrying conductor like this, where this angle theta is equal to 90 degree, then we are going to get the maximum torque. And that is why here you can see this is the term, that is lambda d iq and lambda q id, right? Now here uh, let us see a few things, that is, now before I proceed, I would like to give you the second assignment. Obviously don't worry about the first assignment answer I'll obviously share with you. So what you have to do here, it's very simple, that you have to find out the steady state expression of means steady state equation of our machine, and also you have to obtain the steady state circuit representation of our machine. Like in steady state, let me give you some few hints that will help you. So the task I would like to give you, that you have to find out the steady state equation of synchronous machine. Here expression like the first you have to write the voltage equation like Vs, Vbs, Vcs, and here it should become d theta f dt is equal to omega r. You can take omega r, that won't cause much problem. Then you have to find out the balanced steady state phasor relationship for the synchronous machine. And finally, what you need to do is the balanced steady state equation. So balanced steady state equation, you have to follow all these same things, simple things. And finally, as far I remember, I have also discussed this case. So your assignment is to derive all these equation for steady state operation of synchronous machine, right? So this is your task or this assignment, and also you have to find out the steady state circuit diagram. That means what type of change do you expect here in d axis for steady state. One obvious hints, let me show you. In case of steady state, what do you think? That in case of steady state, what we will have? We will have a constant value of current I f dash here. So we can write here a constant current where if double dash is constant. Similarly, in case of steady state, what you can expect, that the current, this current, this we should connect one current source here with current value IKD double dash is equal to 0. So that you have to figure out, and if you are not at all to do all this means all this exercise, or means take this all this kind of stress, Then the easiest thing for you is to, let me tell you, I have already sent one means DJView file in your Netflix portal a long back. I cannot tell you the date right now. Then I have to again go to Netflix and check the means date. But you can download that book, Chi Moon Ong, Dynamic Simulation of Electric Machinery, and you will find that steady state operation, article 7.4, and that will surely help you to means uh, derive the steady state model of the synchronous machine. But it is desirable that without blindly following that book, you try to derive your own equation based on the article. And also I have shared a video lecture that how to derive steady state model for any circuit. So you try to derive steady state model of synchronous machine as well as try to draw the circuit diagram, and then finally try to prove this, the expression where delta is your power angle. What is power angle we all know, and even if we forget, that is our own responsibility to learn and memorize that this one is, sorry, that we have to find out the expression of tan delta, right? Tan delta is equal to rs im sin theta pf. This theta pf is our power factor, and here it should be omega e, where omega is the speed of your electrical rotating field, cos theta pf here. Okay, and so you can write the expression of tan delta. Actually, it's a bit difficult for me to write it on screen. If you cannot figure it out, then I will help you. And obviously, the easiest way that you will also prefer to do is to directly go to page number 291 of that DJView file and copy it from there. But I will be more than happy that if you can give a try to derive the equation by your own effort, right? Here are a few, here a few things that we must consider, because t make greater than 0 means you are giving mechanical power to your system. Then it implies that your machine is generating, right? And t make greater than 0 means your t make and omega both are in same direction. Here t make greater than 0 means, right? Now this means T damp is the torque produced by our damper winding. Now here we are considering only that means lossless machine. If we consider any machine with loss, then we have to another few additional terms here, like instead of having only j d omega rm dt will have some, sorry, not p loss, it should be uh, t loss, which is also a function of omega Rm, right? That means her torque, and obviously the left hand side will remain same, that is Tm plus T make minus T damp. So this gives us the dynamics of our synchronous machine. So if the left side is greater than 0, then only machine will undergo some kind of, means greater than or less than 0, then the machine will deviate from its steady state and will undergo some kind of, means either acceleration or retardation. And this delta t, as we know, this is the power angle, right? Here one thing you must note, that in case of synchronous machine, your omega r is equal to omega e, and this is always means true for synchronous machine, except a few case, means in your transient case, and this omega r is equal to omega e always. So this omega r minus omega e, you can see here from this line that delta t is equal to theta r minus theta et. It is in electrical radian, that can be written as integration of angular speed plus initial angle difference theta r minus theta 0. Now if we do that, what will be getting, this term omega e is constant, and in most of the cases your omega r is also constant, except, means let me write it very clearly. Sorry. This is during steady state, but during transient it is not is equal to 0. Means in case of transient, what you will have, you will have either greater than 0 or less than 0. Greater than 0 implies your machine is in accelerating stage, and it is in means retarding stage. So this d omega dt, we can write it, the sleep omega r minus omega e, means sleep is also only during transient. Sleep cannot be observed during steady state. This sleep omega rt minus omega e is equal to this total thing Tm plus T make minus T damp. Now another thing here, it is very interesting to note that this your d omega r dt, that I must mention here. Previously we have just this qualitative assessment or qualitative discussion we have made to understand that damper winding is always opposing any transient state or any change in our speed. But here it is very clearly evident from this equation that it is always minus T damp. So whether it is positive or negative, your T damp is always trying to oppose your rate of change of speed. That means whenever your d omega, or more precisely, if your d omega dt greater than 0, then this t damp is also greater than 0, and this t damp greater than 0 means your total change will be getting reduced. And similarly, when d omega dt is less than 0, you will have a less than 0 term here, and that will also means change the means will try to control the rate of change of d omega dt. Okay. In our next video, we'll see how we can have the transient model for our system, right?